All right, hi guys. Just in a second, we're going to start the meeting. Thank you all for coming. This is going to be about natural language processing. It's going to be a pretty basic overview. We're not going to go super in depth because this is like a really deep field within ML. We're going to explain the basics of it, and you guys should be able to build a classification model like that. So hopefully that'll be cool. By the way, just out of curiosity, who has finals this week? Sorry, I'm not finals, midterms. Next week? All right, so you guys look pretty busy. All right. Thank you for making some time for this, guys. Are there any really hard midterms coming up? Okay, so that's fine. Hey, okay, hold on a second. All right, looks like everyone's sat down, so let's get started. So today I'm going to introduce natural language processing, and just a couple people over there. All right, so we're going to start by just introducing our problem. I wanted to drive this by an actual problem statement instead of just throwing a bunch of terms to you guys. So let's start by introducing the problem that we're going to solve. So we have a data set of a huge number of reviews from Amazon. So these are reviews about office products, so things like printers, staplers, stuff like that. And we're given a lot of text, which is what's in the review, and we're also given the associated number of stars. Our problem for today is we want to predict, based on the text in a review, can we predict whether or not it was a good review or a bad review? So was it positive or was it negative? The original data set actually had a range of values between 1 and 5 stars, but I tried solving that problem and it turns out you can't really get good accuracy. A lot of the data is messy, and even with a BERT model, you can't get better than plus or minus 0.4 stars. So it's not that great. So, what's BERT? BERT is like pretty much the best language model right now. Google trained it on like a couple hundred million words, and it's a fully pre-trained transform model that you can use. And we're not going to do that in this lecture, but if you guys want to, the code that we have can actually take BERT as one of the layers. And if you want, you can see how BERT works against a real problem. It's actually really interesting. We're going to be using a much simpler architecture, but if you guys want to use BERT, go for it. So that's our problem. We have a bunch of reviews and we have the number of stars. Now, we're going to simplify the problem by making it a binary classification problem. We're going to set it to where we're going to classify whether or not it has more than 3 stars or less than 3 stars, or less than or equal to 3 stars. The reason for that is so we can get something resembling good accuracy. This model will get mauled on the actual problem. So we're going to stick to a simpler problem. All right, so now that we've introduced the problem, let's move on to the next slide. So we've actually gone over binary classification a couple times in this semester. We've gone over a couple different algorithms we can use, and these include logistic regression, k-nearest neighbors, SVMs, and of course, by Dr. Jasky, a full multi-layer perceptron. Now, we could technically use any of these, but as we'll see in a second, the nature of the problem kind of limits us to one of these. So just to connect this to our previous lectures, this is a binary classification problem. Okay, so we could try and just take our words and directly shove into a model and see if it works. The problem that we have to solve, like a big problem we have to solve, is how can we take words, which are characters, and convert them into numbers that our model can actually use. All the models we talked about, like from all of our non-deep models to our deep neural networks, require numerical inputs. How are we going to take words, which are very much not numbers, and convert them into numbers? Right here we have the problem. So if we're given a sentence of some arbitrary length, how do we take that and convert that into some form that we can feed into a network? We're going to explain that over the next couple slides, but just think about that for a second. How would you go about solving this problem by yourself? We're going to start with a naive solution that's like kind of bad, and then we're going to get to a good one. So let's start with the crappy solution. So the really bad solution, the naive approach, is let's take every single word and assign it a number. So let's say that we just take a iterator, go over the entire text training set, and assign every unique word a number. So if you look at this case, for example, we have our 2 pieces of text here. The mouse ran up the clock, and the mouse ran down. We assign every single word a unique number. And once we have that number, we can then convert every sentence into a list of numbers. each number corresponds to one of the words in that sentence. Technically, this is a solution to the problem. We have turned it into a bunch of numbers. But while this does work, there are a bunch of problems we have to solve with this representation. Are there any questions so far? All right, good. We just started, so hopefully there's not too many questions just yet. All right. So let's talk about the problems with this approach. The first thing is, while we did turn it into numbers, those numbers are completely meaningless. We could order those numbers in any order we wanted, and that's not going to tell us anything. So yeah, our model knows that there are some words in here and they were repeated in some order, but it has no idea what those words are, what they mean, what language it is, nothing. And so it would be better if we could actually tell the model about what each word means and give that as a bunch of inputs. And so if we gave this list or that list to a model, we're basically saying, go learn English by yourself without any training data. Go figure out what each word is, go figure out the order, and then figure out how to classify them. That is a very challenging problem to solve, and it's kind of dumb to try and solve that. So let's make it a little bit simpler. So what we're trying to do is take every word and map it to a vector or some type of container of numbers that tells us about what each word actually means. All right. So we're going to introduce a really big concept right now, and this is word embeddings. Again, we're not going to go super in depth because, like, if you go super in depth, there's a bunch of research on this. We have some master students, they might be able to talk about this in a bit, but I'm going to talk about the very basics of word embeddings and how exactly it works. So right here, we have an overview of a full pipeline for taking words and turning it into vectors. So this first part we already covered. Taking all of our words and turning them into numbers based on which word they are. So the new part of this, the embedding part of this, comes over here. So we have this magical embedding layer, which we'll explain in a second, and we have a bunch of output vectors. Now, if you look at this and compare it to this, there's way more data contained in these. It's just by looking at how many numbers there are. And as we'll see in a second, these actually have a lot more meaning compared to those. So let's go over exactly how a word embedding works, because we would rather have a huge amount of data than a small amount of data. So let's get started. Are there any questions now?
Why would you go directly from the list of words to?
So this will explain a little bit more in a second. The quick answer is that this embedding layer is actually a neural network on its own. And the problem is we just said you can't put words into neural networks. And so we can't just shove these words directly into the embedding layer. We have to have some starting set of numbers, and then we can make a more precise set of numbers. That's the reason why we have to do that, because then we basically just created a new problem on top of what we already have. All right. So this is a quick slide on how embeddings work. So I'm going to break this apart, so hopefully we understand everything. So there are a bunch of different ways to do embedding. So if you get more advanced, you learn about different types of models like word2vec and fast text, and there's one more I'm missing. Glove, actually. Those are the three main ones. But we're just going to focus on the general concept. We're not going to go into each one. So the general idea behind an embedding algorithm is, let's train a model that takes in some text and train it on a task that requires it to learn about what each word means. So let's look at this particular problem. So we have this sentence up there. Let's pretend that's all the text we have. What we're going to train our model to do is, if I give you this word, airplane, tell me what words are closely related to that. In this case, what words show up at similar places in the sentence. If you look at that sentence up there, next to airplane are is, my, music. Those are the three outputs we have over here. This might seem really useless on a small piece of text, and it is, but if you train it on a couple 100,000 words, it'll learn some really interesting relationships between words. So things like, if you have a word like a color, it'll be able to tell you that objects are commonly in that context. Because if you have a color like red, you're usually describing something like a house or something like that, right? And so if we train an embedding on a really big data set, it'll learn how to do basically word association. If I give you this word, tell me what words come to your mind. If you train it on enough data, it becomes really accurate, right? Now let's focus a little bit more on this particular model. Now, right now, this is cool. Like, yeah, we can figure out what word association exists, but really our problem is, if I give you a word, I want a really good representation of that word. So let's focus on the last two layers for right now. Let's ignore the input. So at the output layer, our model is able to tell us exactly what words are associated with this word. using just this layer's data. Remember, in a feed-forward network, or excluding the weird ones, the output of one layer is just a function of the layer before it. So it was able to make this decision based on the data in this layer. And so it's able to tell us what words are related to this word based on what's in here. So just reasoning, we can say that whatever information is in this layer is sufficient to tell us what type of word it is. It tells us if it's a descriptor, if it's a verb, and exactly what type of descriptor it is, right? So maybe it's a color, maybe it's a descriptor for a person. All of that is somehow encoded in here. And so coming back to our problem, because we want it encoded, this layer right here actually has all of our information. And so the next part of an embedding after training it, we're going to take off the output layer. We're just going to keep this input layer, this hidden layer right here. This has all the information we need to be able to figure out what a word is. So if I feed in a color, it'll give me a particular representation that's really good. That was a lot that I just said. Are there any questions right now? I'm asking for some. Okay. Yep.
So I was wondering, does you can choose how many basically, like how big the hidden layer is.
Yeah.
You start how big like the output of the embedded is.
Perfect. Yeah. Yes, you can. So actually, if you look at different embedding algorithms, there's actually different sizes. So we're working with one in the workshop that's 96 long. Google's one's 300 long, and some go even bigger than that. The more dimensions, the more accurate the output. But the issue is it's more challenging to work with. It's just a lot of data. I saw some other questions. Yep. Yeah. Yeah, so this whole thing is on these first two layers right here are the embedding algorithm. We take our input and then we output a vector which has all of our data in it. So the cost function is basically, so okay, actually, before I explain that, I have to explain how it outputs it because then we can go over that. So are there any questions about what I've explained so far, except for cost function, because that will require a bit more information.
This is a simple question. But have the diagram I have of the window display
Oh, those up there. So when you're training your word embedding, you have to decide how many words you want it to predict. So that window is basically how many other words you want us to predict. So if our window size is 4 and we input 1, we want it to output the other 3 words in that sliding window. And the idea is that if you make it too big, that if making a prediction that's way too large, you can't have a whole sentence based on one word. If you make it too small, it's not very hard of a problem to solve. So picking that window size, basically how much data do you want to extract from that individual word? Any other questions?
It's like, what does the training data look like for an effective embedding?
So okay, let's actually go to the next slide because this is actually explaining exactly how this works. So when we're inputting our words and also outputting our outputs, we're representing them as what are called one-hot encoded vectors. This is a big word, so let's just look at this example right here. If we have a data set with 2 possible outputs, so male or female for gender, for each one of our vectors, we're just going to have 2 dimensions. So one represents male, one represents female. To encode our data, we can set one of them to 1 and the rest to 0. So if we want to say that, hey, this data point is male, set the male column or male dimension to 1 and female dimension to 0. This can expand to as many dimensions as you want, and it allows you to basically select one of a bunch of different outputs. All right, that is basically how we encode our data. Now, to go back to our cost function question, how do we determine how bad our model is? We're basically going to compare the output that our model gives to the expected output as a one-hot vector. There's a function, the softmax function you can use to compare 2 outputs. That's used to determine how wrong your current model is. So does that explain the question? All right, perfect. Yeah, that needs a bit more information to understand how that works. So I just explained this. Are there any questions on this? Because this is kind of a big concept. Any questions about one-hot encoding? Yeah. Genetic data?
Yeah, so actually we look at like the training data that
I'm not familiar with that, but I believe Noam is actually quite interested. Do you know anything about that?
I just got started looking at a lot of genetic data.
Yeah. Oh, sorry. Yep. Up there.
just as a comment, like the sequence data, like there are already papers that talk about like continuous distributed representation for protein sequence. You have their own like bio.
Oh, bio2, that's interesting. Okay, I've never heard of that one. I'll go. Okay, sounds good. I'll go with that. All right. So for this case, we're just dealing with one vector. We're not dealing with sequences of vectors unless we're doing the whole sentence. But for right now, we're just dealing with one word. So we're just dealing with one vector at a time. All right. So now that we've explained how we input data into our model, we're also going to tell one more thing that's important for our workshop. And that is how to take a number and represent it as a one-hot encoded vector. So if you have a list of numbers like this, 1, 4, 2, 0, 3, and you want to encode it as a one-hot vector, what you're going to do is basically treat those like the indexes in a list. So if we have 1, we're going to set the second column in our first list to 1 because it's 0 indexed. From there, for 4, we set the last one. 2, set this one. 0, the first one. And this allows us to basically take a bunch of numbers and turn them into one-hot vectors. The reason we're going to need this is going to show up in 1 second. And actually, we can take a look at it right here. Right here, we can all our words and represent them as numbers. But we just explained that this takes one-hot inputs. That's why we need to convert our numbers into one-hot inputs. And the reason we don't just output them like that, a 10,000 long list with like 16-bit integers, that's 16 kilobits per list. That's a lot of data. Instead, if you just have one number and then convert it on the fly, saves a lot of memory, which on large tasks that can help a lot. Okay. Are there any questions about that? Because I did say a lot just now.
The reason we're using ones and zeros, even though it should look like it maybe takes up more space, is because the numbers themselves would be bigger than when we're using just zeros and ones in memory.
I'm sorry?
I'm confused as to why we're using, like, instead of feeding the numbers indirectly, we're feeding the index, right, within the array, right, to mark like the exact same number that we would normally feed.
Oh, that's mostly because for our network, it helps a lot if we input it as a list of numbers instead of just one continuous value. That allows us to basically select one branch of weights. Basically, that's the concept. Oh yeah. Sorry.
No, this thing is so like you listed like one number, correct?
Yeah.
So that doesn't but that includes it's supposed to order on the order. But we don't care about the order. We just care about like this vector corresponds to this. It doesn't need to be on order.
Yeah, well, we're dealing with it on a word-by-word basis in this case, so we're not too worried about order. Yeah.
So that, I believe that's why remove ordering from, I don't know, maybe that, that was my context.
So for individual inputs, we don't have to worry too much about inputting any ordering data. Also, with this, oftentimes it's just alphabetically set, and so the actual index that we set doesn't really impact the ordering. So that's good. That's a good question, but we're running on word by word, so we're not too worried about that. All right, sounds good. All right, perfect. Yeah, there might be other reasons like when we're encoded. The one that I've heard the most about is also training performance. So interesting. All right. So we've just gone over how to take numbers and represent them as one-hot vectors. And this is actually a diagram of what a full embedding model looks like. So I mentioned that it takes a one-hot input. So this case is a 10,000 long input, which means 10,000 different words in our language. Our output is also 10,000. That's the same number of words. And this is the embedding layer. Someone asked about the length of the embedding layer. We can change it as much as you want. This is 300, but you can have it at 90 or whatever you want. And the more neurons you add here, the more accurate your representation is. Okay, does this make sense, everybody? Yeah.
Just like for you to clarify what the length of the input vector is in relation to the input.
So the length of bits is actually just the number of words we support in our vocabulary, and the one we select is just whichever word we're currently thinking about. All right. Any other questions? Okay, I'm looking right ahead. Okay, perfect. Doesn't look like there's any questions right now. Okay, so the reason I went through that whole explanation of why we're converting words to vectors is just to explain this stage right here. We have our mapping words to integers, and then we then have to convert these integers into one-hot vectors. That's to put it into our embedding layer. And this component right here is actually known as the vectorizer. So its job is to basically go over all of your text data, basically understand every single word in there, and then assign each one a unique integer. From there, you can do the rest of your tasks. So turning it into your embedding and then classifying it. That's basically just to learn the vocabulary. And for any specific task, you could have more or less words in here, and that allows you to save space if you don't need a full embedding. Okay, any questions about that? Oh, all right. Let's see if we have some chat in here. Oh, never mind.
Is just doing that first step, right?
Yeah, so this right here is the vectorizer. So we're taking all the words and converting them to numbers, which is our representation. Okay. Now that we've explained that, we should be able to move on to the next slide. Oh, mine, there it is. All right, so we've gone over most of the basic parts of how an embedding works. Again, it goes more in depth than that, but that's how we're going to cover it. Now we're going to just talk about some other tricks that are commonly used in NLP. So we're using a package called Spacey, so it does a lot of this for us, but still helpful for us to understand what processes are happening underneath the hood. So we're going to focus on two main ones, tokenization and lemmatization. The first one is tokenization. If we're given a sequence of words, this gives a sentence, we want to basically break it apart into a bunch of different tokens. So this could be a word, or it could be a piece of punctuation, or whatever it is. And Spacey does this for us, but there's a lot of different rules. You can use different schemes to break it up into a bunch of words. And Spacey does this with different rules based on what's remaining in the list. And so we get this really clean output. If you want to build it yourself, most of them are rules-based. You just have to keep doing it until you get a clean output. As well, for our data set, we're actually ignoring the solution. Now we just focus on the words. Okay, are there any questions about this stage? Okay, sounds good. So again, this is done by Spacey on the fly, but if you want to implement this by yourself, it's all rules-based, and also you could increase performance. All right, so we're going to cover one more thing, which is lemmatization. This is a technique that allows us to take multiple forms of one word and convert it into one actual word. And the reason we want that is that if we have a bunch of different words like changes, these basically mean the same thing. But if we don't lematize, we're going to have all 5 of them in our vocabulary. This gives us a much longer vocabulary, which just decreases performance. As well, we don't really need all that extra data. And so lemmatization allows us to normalize everything into the shortest representation. The other one's called stemming. This is an older way of doing it. It just cuts off the end of it. It's generally outperformed by lemmatization. And so Spacey by default uses lemmatization instead. And both of them try and do the same thing. You're trying to take a word in multiple forms, convert it to one representation. Okay. That's all we have for lemmatization. Are there any questions about that? Oh. Yeah, okay. For different problems within NLP, you may or may not need different parts. So one other common process called stop word removal. It turns out that sentiment analysis is really sensitive to stop word removal, and so we're not going to do that. But yeah, different problems may require different operations. But for our task, we're using lemmatization just to decrease word size. Vocab size. That's just to make it run faster. All right. Any comments on that? Oh. For that example, I'm not exactly certain because I didn't see the source code, but for most languages, it would actually be much bigger. So I'm assuming that's just a toy language. That's not really like a real data set. Perfect. Okay, so that goes over the 2 main processes we're going to talk about within NLP. And also, I just want to go over the common things that we see in a Spacey pipeline. We use Spacey as a tool to do all this for us, but let's just look at everything in it. So the first thing we do is we do untoken event, which actually takes all of our inputs and actually turns them, actually tokenizes them. The next thing we do is tagging. This tags different parts of speech. Parsers just learn dependencies between different words. Actually, really, we're not really using it for our use case. If you want to use that, it allows you to do custom rules. And then, of course, lematizer. This is what we talked about just now. This just decreases the vocab size by a lot. And any other token effect, these are not enabled in our pipeline. So that goes over all the stuff that Spacey does for us. You can also take do more tasks on top. All right. All right, so that's all we have for this lecture. It's not going too in depth, but there's a lot more resources available. Also, pretty much everything I just covered goes way deeper. Like lemmatization is a whole thing on its own. There's like models for that. So it's really interesting. All right, so that's what we're covering for the lecture. We're now going to go over source code. So if you guys want to pull out your laptops, I'm going to send out a Colab notebook right now. All right, any last questions about the lecture?
So all of these group words, they branch out all these different neurons.
I'm sorry?
Share some
In the embedding layer or on the final layer?
Oh, no, the first layer.
Okay, so in that case, yeah, it would be a longer vocab size. So yeah, there would be more connections between it and the rest of the neurons. Yeah. Yeah, and also that also decreases performance. So if you don't need it, I would recommend like that. That's basically it. All right, so I'm gonna send out this link right now. This is the full setup. Let's see. Yeah, got it. 1 second. Okay, share, and then I'm gonna set everyone to viewers. So 1 sec. Oh, anyone with the link, viewer, copy link. All right. Just for, all right, I just sent it in general. All right. I show more general announcements. Everyone. All right. Oh, send now. All right, just sent it out. All right, so for this workshop, I'm not starting just yet, just in context. I've already pre-built all this stuff. I think it'll take a long time for us to go over this. Also, training this model actually takes a long time. So we're just gonna go over it, how I did it, and then if you guys want to play around with this at home and train it on your own time, feel free. Also, there's a lot of cool stuff you can do with the actual model at the end of it. So I'll go over it. All right, so it looks like everyone sat down. Let's get started with this workshop. It's gonna be a little bit shorter than normal. I'm gonna be going over it, but if you guys want to play around with this, feel free. So imports, there's nothing really special here. We're just importing NumPy. We're using Keras for our neural network. That's pretty standard. It's like an easy one to use. Text vectorization, embedding. These are the two things that I mentioned towards the end of it. Text vectorization is the one that takes words and represents as numbers, and the embedding layer is our conversion to actual vectors. TensorFlow is just a dependency, and then yeah, Spacey, our big component that does a lot of the heavy lifting. Spacey has inbuilt word vectors that we're gonna load in, but something cool that you guys might want to play around with is you can actually train your own word vectors. So there's libraries that allow you to do that, or you can do it from scratch if you're really brave, and see what performance you guys can get. I'm actually really curious on what you guys can do. All right. As well, we have three major components down here. These are just the visualizer embedding. So the first part of this demo is just going to show the visuals for the embedding. So I mentioned a lot of stuff about numbers and vectors. We're going to see how they actually look. All right. The first step is configuring Spacey. This is pretty much in any notebook we're using Spacey. We're going to download the small English language model. We use small just to make it faster, but you can use the large one. There's also one TRF that uses transformers for its embeddings, but we're using small just because it's supported by Colab and also it's pretty easy to use and it has enough data in its embeddings for us to solve this problem. So just downloading it. Sorry? I can elaborate very little because I'm not super good at them. Is anyone here really good at transformers? Any grad students? I need someone's help. All right. Sorry? The question is just general overview of transformers. General overview of transformers.
It's not very much more complicated.
Okay, I'll give it a shot and I'll see how it goes. So transformers are part of a larger set of models called encoder decoders, where you take an input sequence, you encode it into an embedding like this, and then you output another sequence. Normal encoder decoders, as far as I understand, use RNNs. The special feature of transformers is they do it without RNNs, I think. Is that accurate? Yeah. And the benefit is that you can run the whole thing in parallel. So you can have the whole sequence running at the same time. So I think Google used this for translation. It allows you to take every single word in an English sentence, process them all at the same time, and then convert it to like French, for example, simultaneously. And that lets you have a GPU to accelerate the whole process. If you with an RNN, you have to go one by one, which slows your process right down. Is that?
There's a problem. The problem is that even though you can parallelize with a transformer, the memory requirements is always squared compared to an RNN, which is always.
Yeah, so quadratic. I have stuff. Yeah, that's a lot of data, especially if you're dealing with long word vectors. It's pretty problematic. I don't know if they use them for anything else than.
They also use it for computer vision now.
Okay, that would be a problem if you have images doing that. All right, sounds good. Okay, that is interesting. All right.
By the way, guys, we have an entire section in Discord just with papers. And people are just sending really, really cool demos of papers. So if you're ever curious about what's at the cutting edge of ML right now, what are the papers? We post a lot in there. We have another PhD student who posts a lot in there.
Okay.
There's some really cool demos, especially the DALL-E demo. If you guys want to check that out, I'll send that link in your stick.
If you wanted to run the same process.
Which language are you thinking about?
Like Spanish.
Oh, okay, like different language, like okay, English language. Okay, so I'm sorry, human language. All right, so if you want to do it on, if you want to do it on a different language, I think you just retrain on the word vectors you get for that language. Because I'm pretty sure you still use the same process on different languages. You just need to train it on Spanish and then retrain the whole transformer, but you're not going to be doing that in your basement because it takes a lot of effort to do that.
Like Facebook and Google have these like models that train with multiple languages, or they can do translation from English to Spanish and Spanish to English.
Can Bert do that or no? Can Bert do? Okay, Bert can.
It's just you just need to have, like what you said, you just need to train on your own, but you can. If you can do your encoder decoder, you can even have 2 languages or 3 or 4, and then try to predict other language.
All right, well, there you go.
Different languages.
Yeah. Yeah, because I mean, even for this one, we'll see this in a second. We're not going to train our own embedding. We're loading up Spacey's pre-made one. You can also load up Bert's one if you want, but yeah, you can do the same thing for Spanish if you really want to do that. But yeah, that's gonna take a lot of money to train it. All right. So yeah, this is just configuring Spacey. Pretty standard, just downloading stuff. We're gonna download a data set. I put this on S3 so anybody can just download it. And this is a bunch of reviews. You can actually see the shape of it right now. Actually down here, we'll do that later. Basically it has a bunch of columns on the number of stars it has, the name of the reviewer, the text that the reviewer provided, all that stuff, as well as a helpful column. We're not training on that because that's really noisy data, but if you wanted to train a model on that, you could. So that's all available in this data set. So the first thing we're actually going to do is something that I think is kind of cool. We're going to visualize our embeddings. So we saw that our embeddings are these super long vectors, but one of the cool features of embeddings is that words that mean the same thing or close to the same thing show up in similar places. So different colors are closer to each other, whereas like objects and other things are far away. And so I wanted to see if I could visualize that distance. Now, it's not super clean because one of the problems we have is all embeddings are 96 long. We're trying to turn them into 2 dimensions. So that type of dimensionality reduction is going to cause a lot of data loss, but it looks all right. So right here, we're using Spacey to process our document and then perform the whole pipeline on it. We're then going to grab our words and our vectors. So we're using stop word removal and punctuation removal. And right on this line, you can see .lemma. We're actually just taking the lemmatized version of that word and storing it in our list. So that way we don't have plurals or stuff like that. We're also using token vector. It's this really simple interface to a really powerful concept in embeddings. And we store that in a list as well. We convert both of them to NumPy arrays later on. And finally, we use TSNE, which is combined dimensionality reduction and clustering to try and visualize this really big embedding. And this is what it finally looks like. So I plugged in a CNN article as the input, and we can see like fulfillment, commerce show up in a similar place. Let's see what else is here. Yeah, there's some weird ones. Again, that's caused by the noise in our dimensionality reduction. But for example, like companies show up in similar places, recent news show up in similar places, provide reports show up in similar places, and then like let's see, I think good ones up here. Packing and shipping show up in similar places. So that's just an example of what it looks like. If you did it in 3D or use an embedding that's smaller, you might get a better result than this.
Also reduced by 94 data.
Yeah. Yes. So you're trying to find some patterns on the line to do that reduction. There's some really cool tricks to do that, but on that scale, it's kind of a mess. Sorry? Like as in like bad data, or what is that? Bad data. Okay, so one thing you can do, I know that a couple companies use this, is that they train it in badges and they look at the highest the samples that have abnormally high error, and they take those out of data set. They keep doing that over and over again until they can find a large portion they can train on. But that's not perfect because you could be just taking out really hard cases instead of wrong cases. So I'm not entirely certain how to do it in production on really bad data, but you can definitely look into that. Also, we might have some people send some Discord links about that. So awesome. Any other questions so far? Oh. We lemmatized, we just didn't do deduplication. It's the only reason for that. Yeah. All right. Any other questions? All right. I don't see anybody. All right, perfect. All right. So this is just a visualization. You can do it in 3 dimensions. You can do a bunch of things to make it look better. I just didn't have that much time to do this. So this is what it looks like. And the next thing we're going to do is just solve a classification problem. So the whole point of this workshop was, can we train a model on sentiment analysis? Here's where we do that. So this is just basic stuff. We're just loading in our data set. So if I, so this is our data set. If I just, let's see, comment out the rest of this really quickly, and then just do data frame.head, we should see, oh. Yeah, we should see here. This is our entire data set. So we have reviewer name, reviewer name is just a username. Helpful is, this is actually a fraction, which is a really weird way of storing a fraction, but it tells us how helpful that review was. We have the actual text, overall score, score in stars, a summary, and then unit review time and review time. These are very useful. Another fun problem that I did not tackle is if you wanted to take text and summarize it instead, you can feel free to tackle that. I don't know how to solve that one, but if you guys want to try that out, go for it. It's still in this data set. For us, we're going to use overall, and we're going to convert this into a binary problem. So let's do that right now. So let me uncomment everything really quickly. So first thing we're doing is we're dropping columns that aren't useful. What's going to go down here? We don't need our review time or our unit review time. We don't need helpful because we're not training on that, and we don't need rewriting or any time. And we're just dropping all those columns. Next thing we're going to do is actually convert our problem from a continuous problem to a binary problem. So it's what overall class function. What it does is if our overall range is greater than 3, return a class of 1, otherwise return 0. And we apply that to every single row, and that way we can convert it into an easier problem. And if I go ahead and do dot head after that, let me just comment out, run. Oh, it's gonna take a while because Colab is slow. Here we go. So I dropped a bunch of the columns, as you can see, and also if you look at overall, we only have 1s and 0s. This is a much easier problem to solve. All right. The last thing we're gonna do in this cell is just take all our words and pull them into a numpy array. I had a problem. Oh, yep. For the way I'm tackling it, no, but you could use it if you can find any useful information. Like maybe if you wanted to figure out like how serious someone was, you could look at their name and see if it's like a good name or not. I'm not sure how you'd use that, so I took it out. It was easier. But yeah, you could use it if you wanted to. I saw some other hands, or was I seeing something that's not there? Oh, okay, we have that to there. Oh, I took out reviewer ID. Interesting. All right. Reviewer. Yeah, no, it's fine. Yeah, I just forgot to take out that one column. Should run right now. And also take out this last one so we can verify that we dropped our other column. And there we go. We've taken out everything that's not useful except for summary. Yeah, so this is all this column does. Sorry, this cell does. It just drops on this column. The last line that we're gonna do is we're gonna take our overall score and bring it out into a numpy array. The reason for that is I had a problem when I was building this on myself that if I tried to pull the train data set directly out of it the data frame, it would transfer too much data at once. I can't figure out why that's the case, but I found that pulling it out into a numpy array early and then just using that actually helps a lot. I'm not sure if you guys have seen that before, just using pandas as the source. Pulling it out seems to fix it, so that's why we're doing that. Everything up here is just basic data processing. This is like the interesting part that is kind of NLP. So the first thing we're going to do is we're going to declare text vectorization layer. This is that layer I was talking about with vectorizers. We're just going to declare it right now. And this line, these two lines right here are pretty important. So dot adapt, what it does is it goes over the entire column of text, finds every single unique word, and assigns a number to that. So that's the actual part of it that assigns numbers to each of our words. Dot get vocabulary, it just pulls out every unique word found. And that way we can iterate over in our next step. So all that does is it pulls out all the words we found. The next section we're going to do is we're actually generating our embedding layer. So first we're going to do is you want to know how many tokens we have or how many words do we have. We're just taking the length of our vocabulary. The next thing is we want to know how many dimensions does our embedding actually have. So we're just running our pipeline on the word the, and we're just finding the length of the vector. Just for this one, it's 96, but based on which language model you use, you can get much longer. 300 is the longest one. This one's 96 though. And finally, the reason we needed that is because we're actually going to create what's called an embedding matrix. And this is basically just a lookup for what embedding map to what words. And we're initializing the number of words we have and the length of our embedding. That way we can store it in there. Any questions about that? Good. So again, just a quick overcap, review. We're just adapting our vector, our vectorizer, and then just basically making an empty matrix. That way we can store all of our vectors in there. Then what we're going to do is we're going to iterate over every single word in our vocabulary. And assuming it's not an empty word, we're just going to run our pipeline and store the vector in our matrix. What this is doing is populating our embedding matrix with the embeddings from this pre-trained embedding. If we did this manually, we'd have to train our own embedding model. That takes a really long time. So instead, we want to store our pre-made one. So this is an example of called transfer learning, where you take a pre-trained model and put it on, or a pre-trained data set and put it inside your own. This is just loading up our matrix. And this is our embedding layer. Again, we're taking the number of tokens, that's just how we have the length of our embedding. And what we're doing here is we're passing in a matrix as an initializer. So instead of random values for initialization, we're going to use these pre-trained vectors. That's just going to allow us to skip the whole training process. We're also going to set trainable to false. We don't have a big enough data set that we can improve these embeddings. So we're just going to leave it as false because we're only training on a couple hundred examples. Now, what we've basically done is we've created our vectorizer and created our embedding layer. Any questions about that? For our use case, we don't need more than one because once we've converted our word, each word into an embedding, we don't need to do anything else. I don't know if that many applications use more than one embedding layer. Like, what's that used for commonly? I don't believe it helps to have more than one embedding layer because the point of the embedding layer is to convert words to vectors. There's no benefit in adding more of those because you already have vectors at that point. Right. Okay. So hopefully that question is dealt with. Now that we've created all of our word processing, we can now actually build our model. So this is a really basic architecture. We just defining our inputs as shape 1 and then whatever input it wants. We're then passing in our vectorizer and our embedding layers, the first two layers. That allows us to put words directly into it. And then we're just going to use one dense layer, so 100 radial units. You can feel free to play around with whatever other units you want to use. I know that LSTMs have really good accuracy. CNNs don't do that well on this one. And also you can play around with having more units, more layers, batch optimization, whatever you guys want. I'm trying with 100 because it's simple architecture and it actually gets pretty good accuracy. And finally, we're just gonna add on an output. So this is because it's a binary problem, we just need one sigmoid and that works out just fine. We're defining our model. We're gonna get a summary, which is right here. And then we're just gonna compile it. And then we're gonna fit it. So for compilation, we're using Atom. Generally, that fits the fastest for this problem. You can play around with other ones though, obviously. For loss, we're using binary cross entropy. It's a binary problem. And for metrics, for the regression problem, I use RMSE. For this one, speech accuracy works just fine. And then we're going to validate by passing in validation split 0.3. That means that 30% of our data is used for validation. And we're also going to get the accuracy on that data. So we're just going to fit with batch size 32, 2 epochs, and we can see that our validation accuracy by 82%. So for such a basic architecture and such a little training, it works pretty well. Again, feel free to try out with more advanced models. You guys, I know that you can get this one close to like 95%-ish with really cool models. Yeah. So if you want to do this by hand, there's not too much. Just play around with different like types of layers. You can use recurrent layers. If you guys want to do automated tuning, then you can use, for this problem, you could probably use Hyperband, which is an automatic tuner, or you can use Bayesian search and just try a bunch of them for you. But yeah, there's not too much I can say about optimizing it. I know that you can also play around with putting BERT in here if you want, because I've seen that. That has some of the best accuracy on this problem. But I haven't done that just for you guys to play around with that. So hopefully you guys can take it home. By the way, Colab is really slow, by the way. Calculating our word vectors is super slow. So I would say run this locally if you can. It takes like 10 minutes on a local machine. Are there any questions about this whole demo? All right, I've sent out this Colab so you can download it and play around with it. Also, I'll be up here to talk to people. Also, there's a couple people I want to talk with right now.
Do you mind just running like a random like sentence or something like a triangle Amazon review just so we can see the output of a prediction?
Yeah, I can try it. I mean, I'm not sure if it's gonna work very well. Let's see. Let me just grab. Let's see. Let me just grab some example text document up here. I think with really short ones, it's going to have bad accuracy is the only issue. So let's just see. Yeah, sure. I'll run that. Oh, yeah, I think I have to pass in an array. 1 second. Oh, and then one more bracket, I believe. Yep, there it is. Yeah, so outputs, a couple outputs. I think it's because I'm not passing it in correctly. It needs Basically registered as one sentence, but sorry? So 1 is a good class, 0 is a bad class, but just passing it like that, it seems to just take each word as its own input. So I'll have to play around with that and see how to get it to work. Because on our training data set, it's able to get really good accuracy. I just have to see how to format it properly. Any questions about that? All right, sounds good. I'll be up here for any questions if you guys have any. All right. Zoom people, I'll be out of here. Oh, stop. You can take that.